So you book a luxury cruise to the end of the earth, right? And there's this expectation of total engineered safety. You picture the pristine decks, the endless buffets, the ocean breeze.
Oh, yeah, a floating bubble.
Exactly, a bubble. You're stepping into this environment that is completely isolated from all the chaos of the natural world. But today, well, our mission in this deep dive is to basically pop that bubble.
We are definitely popping it today.
Yeah. We're unpacking a really urgent, unfolding global health event. Specifically, the unprecedented May 2026 hantavirus outbreak on the cruise ship MV Hondius.
Right.
And we're going to explore, the biology of the virus itself, the microscopic countermeasures being developed, and really the cutting-edge global science racing to neutralize these zoonotic threats before they become the next pandemic.
Yeah, and to map out this whole situation, we're synthesizing a really massive stack of real-time intelligence. So we've got epidemiological data from the World Health Organization's disease outbreak news.
Which is pretty fresh data.
It's very fresh, alongside technical reports from the European Center for Disease Prevention and Control and the Pan American Health Organization. And we're pairing all of that with historical context from Lex.
Right.
Plus, we're diving into the laboratory breakthroughs happening literally right now at the French agency ANRS, MIE, the Global Ecological Mapping Initiative, Project ARHA, and Canada's Vaccine and Infectious Disease Organization, or VIDO.
It's a lot of ground to cover. But let's start with the cinematic, almost terrifying scenario unfolding in the Atlantic.
Yeah, it really is like a movie.
It is. So picture MV Hondius. It's this Dutch-flagged luxury cruise ship. On April 1st, 2026, it leaves Ushuaia, Argentina. That's, the southern tip of the world.
Right, heading across the Atlantic towards Cabo Verde.
Exactly.
Yeah.
And the ship is carrying 147 passengers and crew from 23 different countries. And somewhere in those first few weeks, this totally isolated, highly controlled vessel turns into the site of a deadly medical emergency.
Yeah, and the timeline here, it really reveals how quickly a localized exposure becomes just a massive international crisis. The working hypothesis right now is that the index case, a Dutch passenger, we can just call case 1, actually acquired the infection before ever stepping foot on the ship.
Wait, really? So before the cruise even started?
Yeah. He had been traveling for 3 months across Argentina, Chile, and Uruguay. Epidemiologists traced his movements, and they noted that he and his partner were birdwatching in rural Patagonia.
Okay, bird watching.
Right. And he developed symptoms on April 6th and tragically died on board the ship just 5 days later, on April 11th.
Wow. Just 5 days. And the containment completely fractures at that point, right?
Yeah.
Because the infection didn't just stop with him.
No, it didn't. His partner, Case 2, disembarked at St. Helena on April 24th, and she was presenting with really severe gastrointestinal symptoms.
Oh, man.
And her condition deteriorated incredibly rapidly during a medical evacuation flight to Johannesburg. She ended up passing away in a clinic there.
That's awful.
It is. And by early May, the World Health Organization is tracking a cluster of 8 confirmed cases, which includes a ship doctor and a local guide, with 3 deaths total.
So that translates to what? An alarming 38% case fatality ratio?
Exactly. 38%.
The logistics of responding to a pathogen that's lethal on a ship are just mind-boggling. The Hondius ends up anchored off the coast of Cabo Verde.
Right.
And suddenly you have this massive emergency international coordination. You've got health authorities from Argentina, Chile, South Africa, the Netherlands, Switzerland, the UK, Germany, Spain.
It's a massive undertaking.
Seriously, they're medically evacuating critically ill patients to ICUs across different continents, flying postmortem samples to the Netherlands for immediate genomic sequencing. And the passengers are just confined to their cabins, trying to physically distance on a vessel that's literally designed for socializing.
Yeah, it's a nightmare scenario.
But wait, let me push back on the mechanics of this outbreak for a second, because something doesn't really add up here.
Okay, what's that?
Well, cruise ships have famously tight quarters, yes. But hantavirus, at least according to standard medical textbooks, comes exclusively from rodents, right?
That's the traditional understanding, yes.
Right, like the mechanism of infection is breathing in dust contaminated with aerosolized mouse droppings.
Yeah.
So did this luxury cruise ship have some sort of catastrophic, undetected rat infestation on board?
Well, see, that is the most logical assumption based on decades of virology. But it's exactly why this specific outbreak is so terrifying to public health officials.
Why?
Because there was zero evidence of an onboard rodent infestation. None. When the laboratories, specifically the National Institute for Communicable Diseases in South Africa and the Geneva University hospitals, when they sequenced the viral samples from the patients, they identified it as the Andes strain.
Oh, so the specific strain changes the transmission rules.
Entirely. Out of the roughly 38 known species of hantavirus globally, the Andes strain, which is endemic to southern Argentina and Chile, is the only one documented to allow person-to-person transmission through close contact.
Wait, person to person?
Yes. Usually, humans are just a dead-end host for hantaviruses. You know, you inhale the aerosolized droppings, you get sick, but you cannot pass it to your family.
Right, it stops with you.
Exactly. But the Andes strain bypasses that limitation. It can spread between humans through close, prolonged contact, likely through, respiratory droplets or direct contact with bodily fluids.
So we're seeing human-to-human transmission happening among passengers and the crew who are treating the initial cases.
Precisely.
That is wild. I mean, to understand why this specific strain from Patagonia is capable of breaking the rules of typical transmission, I feel like we really have to look at the bizarre family tree of hantaviruses as a whole.
We do, yeah. The hantavirus family, which is formally classified under the genus Orthohantavirus, is basically divided geographically and biologically. We categorize them into two distinct clinical presentations. There's the Old World and New World syndromes.
It kind of sounds like the virus operates like a piece of computer malware, with two completely distinct regional payloads.
That's a really good analogy, actually.
So lay out the Old World payload first. What does that do?
Well, in Europe and Asia, so the Old World, hantaviruses like the Pumala, Sol, and Dubrava strains cause a disease called hemorrhagic fever with renal syndrome, or HFRS.
Okay, renal, so kidneys.
Right. The payload targets the kidneys and the vascular system. Patients experience severe fever, muscle pain, and increased vascular permeability, which basically means their blood vessels start to leak.
Oh, wow.
Yeah, and this eventually leads to kidney dysfunction that can be severe enough to require dialysis. It causes hundreds of thousands of infections globally every year, but the case fatality rate is generally lower, ranging from 0.4% up to maybe 15%, depending on the specific strain.
Okay, so the Old World malware corrupts the computer's cooling system, the kidneys. It does a lot of systemic damage, maybe requires a temporary reboot or external dialysis, but the machine usually survives.
Exactly.
So what happens with the New World payload then?
Well, in the Americas, strains like Sin number in the United States and Andes in South America, they cause Hantavirus cardiopulmonary syndrome, or HCPS.
Cardiopulmonary, so heart and lungs.
Yeah, this payload completely bypasses the kidneys and goes directly for the pulmonary system. It attacks the lungs, causing really rapid, severe respiratory distress. The capillaries in the lungs become highly permeable, and the lungs essentially fill with fluid.
Oh my God.
Yeah, the patient essentially drowns from the inside. It is incredibly dangerous. It has a staggering fatality rate of 30 to 60%.
30 to 60%. So it basically overclocks the motherboard until it burns out. That is absolutely ruthless.
It really is.
Just looking at the numbers from the Pan American Health Organization, they reported that in 2025 alone, there were 229 cases in the Americas, resulting in 59 deaths. I mean, that is a fatality rate of nearly 26% across the region in just a single year.
Yeah, the numbers are sobering. And what's fascinating from a historical perspective is just how long humanity has been dealing with this pathogen without really fully understanding its mechanisms.
Really? How far back does it go?
Well, the first robust clinical description of the renal syndrome actually dates back to the Korean War in the early 1950s.
Wait, the 1950s?
Yeah. Over 3,400 United Nations and American troops were struck by this mysterious bleeding sickness that was accompanied by rapid kidney failure. Roughly 10% of the infected soldiers died, and the medical units were completely baffled.
So just a completely invisible enemy taking out thousands of soldiers.
Exactly. And it wasn't until 1976 that researchers finally managed to isolate the virus. They found it in the lung tissue of a striped field mouse caught near the Hantan River in South Korea.
Oh, the Hantan River. So that is literally where the name Hantavirus comes from.
That's the one.
That is wild. You have this virus taking out soldiers in the 50s, and then decades later, a totally different branch of the same family is causing respiratory failure on a cruise ship in the Atlantic. I mean, sounds invincible.
It does seem that way.
But reading through the structural biology in these sources, the virus actually has a massive physical vulnerability, right? Like, Hantaviruses have a lipid envelope.
They do, yes. They belong to the order Virales, which are all enveloped viruses. So they are surrounded by this protective layer of lipids or fats.
Which means it works exactly like a greasy frying pan in your kitchen sink.
Oh, I like where you're going with this.
Right, like if you just run cold water over a pan coated in bacon grease, absolutely nothing happens. The fat repels the water. But the second you add a single drop of dish soap, the chemical properties of the soap instantly shatter the fat molecules, and the grease just washes right away down the drain.
That is precisely the mechanism, yeah. Because of that fatty lipid envelope, just simple hand washing with soap or using standard alcohol-based hand sanitizers completely dissolves the hantavirus's protective shell.
Wow.
Yeah, once that envelope is compromised, the viral proteins fall apart and the virus is inactivated. It's actually structurally incredibly fragile outside of a host organism.
So let's pause here because this creates a pretty massive paradox.
How so?
Well, if the virus is so easily destroyed by just basic household soap, and if it usually requires a person to be in the exact wrong place at the exact wrong time to inhale aerosolized mouse droppings, why are we still struggling so much to predict and prevent these outbreaks?
Ah, that's the big question. We struggle because we're trying to fight a microscopic enemy while largely ignoring the environmental chessboard it's moving on.
The environment.
Yeah, historically, the scientific community operated on a very strict one virus, one host species paradigm. The working assumption was that the Andes virus only lived in the long-tailed pygmy rice rat, and the Cinnabar virus only lived in the North American deer mouse. It was viewed as this static, predictable relationship.
But the environment is anything but static right now.
Exactly. We're seeing massive anthropogenic, human-caused drivers completely shifting the board. Climate change is altering seasonal rainfall, which leads to explosions in rodent populations. And then massive deforestation, urban expansion, and agricultural consolidation. They're bulldozing wild habitats. So we are forcing human populations and wild rodent populations into much closer, much more frequent contact.
We're basically moving into their living rooms.
Exactly. And because of that intense ecological disruption, the old paradigms are just collapsing. Recent surveillance shows that the one-host rule is completely dead.
Dead. Like completely.
Yeah. Strains like Cinnabar are now being isolated across multiple different rodent populations, and conversely, a single host species, like the multi-mammate rat, which is the primary reservoir for the deadly Lassa fever virus, has recently been found to host at least 7 completely distinct arenaviruses.
7.
Yeah. These rodents are carrying complex cocktails of pathogens, and they're sharing them.
And this brings us to the data gap, I think. Because our surveillance of these wild animal reservoirs seems incredibly fragmented.
Oh, highly fragmented.
Right, like if a researcher in a Brazilian forest catches a mouse, tests it, and finds a new viral strain, that data might just sit in a private spreadsheet somewhere, or a siloed academic journal behind a paywall.
Yeah, and that fragmentation is what turns local spillovers into major blind spots. We just haven't had a unified, systemic way to map where these pathogens are hiding in the wild before they infect humans. But if you look at the Welcome Open Research publication, there's a massive new initiative called Project ARHA that is fundamentally changing how we track this.
Project ARHA. How does that actually work in practice?
So Project ARHA is building a standardized, global, open-access database specifically for arenaviruses and hantaviruses found in wild-caught rodents and shrews.
Okay.
And they aren't just logging the name of the virus, they're pulling together really granular ecological data. So the exact GPS coordinates of where the mouse was caught, the local climate conditions, the elevation, and merging all of that with the genomic sequence of the virus found inside it.
Wow. Okay. So currently, trying to track zoonotic diseases is like trying to predict a global weather system by having random people occasionally look out their living room windows and, mail in a postcard describing the clouds.
That's exactly what it's like.
But Project ARHA is basically building a synchronized global satellite radar system.
Yes, that is the perfect way to visualize it. It's the core of the One Health approach, which recognizes that human health really cannot be separated from animal ecology. Project ARHA aims to create these spatio-temporal maps, tracking these pathogens across both space and time.
So getting ahead of the problem.
Exactly. By doing this, we move from reactive medicine to predictive modeling. We can look at the data, environmental suitability, rodent density, human land use, and we can say, hey, based on these variables, this specific forest edge in Argentina is at extreme risk for an Andes strain spillover event this coming spring.
But all the predictive mapping and satellite radar in the world won't really help the patient who is already hooked up to a ventilator in Johannesburg, right?
No, unfortunately not.
When environmental prevention fails, like when a passenger on the MV Hondius inhales the virus and it actually starts replicating in their lung tissue, we need a biological failsafe.
We do, and the current state of patient care for hantavirus cardiopulmonary syndrome requires a mix of extreme urgency and genuine innovation. Because, as of right now, there are 0 universally approved vaccines. There are 0 specific antiviral treatments.
0.
Still 0. If you contract HCPS, the medical standard of care is entirely intensive supportive management. Physicians will put the patient on a ventilator to basically force oxygen into the failing lungs. They meticulously manage their fluid intake to prevent further pulmonary edema. And in the most severe cases, they use extracorporeal membrane oxygenation, or ECMO.
ECMO, that's where they pump your blood outside of your body, right? And oxygenate it in a machine and then pump it back in, completely bypassing your lungs.
Yes, exactly.
So we're just keeping the body mechanically alive and basically praying the patient's own immune system wins the fight before the organs fail.
Yeah, that's pretty much it. But the good news is the global research infrastructure is evolving rapidly to provide actual weapons for that fight. The French Agency for Emerging Infectious Diseases, ANRSMIE, is doing some phenomenal work on this front.
Okay, what are they working on?
Well, they have an ongoing field project called TRAN-SVI, characterizing the transmission chains of hantaviruses between wildlife and humans on the Yucatan Peninsula. But honestly, their most exciting work is happening at the microscopic level.
So this is where we get into the mechanics of how the virus actually builds itself. Who is leading the charge on figuring out how this pathogen replicates?
There's a major breakthrough from a French researcher and thesis prize winner, Dr. Quentin Durieux-Troiton.
Okay.
He conducted a highly complex structural and functional analysis of the hantavirus replication cycle. And through his research, he was actually able to observe, for the very first time, the physical structure of a hantavirus polymerase.
Wait, so he was finally able to observe the viral polymerase, like the actual biological engine the virus uses to copy its own RNA?
Exactly. You know, viruses can't reproduce on their own. They have to hijack our cellular machinery. But they bring their own polymerase engine to read their viral RNA and build copies so the infection can spread from cell to cell.
Right.
So why is seeing the physical structure of this polymerase such a breakthrough? Because enzymes work like incredibly complex, three-dimensional physical locks and keys. Until Dr. Durieux-Troiton mapped the exact 3D shape of that lock, virologists couldn't design a chemical key to jam it.
Oh, that makes so much sense.
Right. Now, researchers can custom design specific antiviral drugs that slot perfectly into the polymerase, acting like a wrench thrown into the gears. If you physically jam the polymerase, you stop the virus from replicating, halting the disease in its tracks.
That is a massive leap forward for creating an actual cure. And the laboratory innovations aren't isolated to France either. Let's look at the research coming out of Canada's Centre for Pandemic Research. They operate under VIDO, the Vaccine and Infectious Disease Organization, which is actually currently celebrating its 50th anniversary.
Yes, VIDO is doing some incredible things.
Their approach to the hantavirus problem is entirely different, isn't it?
It is. VIDO operates Level 4 containment facilities, which are these highly specialized laboratories designed for handling pathogens that pose the absolute highest risk of serious, untreatable disease.
Level 4, so full biohazard suits, the whole deal.
Exactly. And they are studying hantavirus not just by looking at human infection, but by focusing on the reservoir hosts. A research team led by Dr. Bryce Warner is investigating a phenomenon known as asymptomatic persistence.
Wait, let's unpack this because the biology here is just staggering. The North American deer mouse carries the Synombra virus. The virus is actively replicating inside the mouse, shedding in the mouse's saliva and droppings, and yet the mouse's immune system just, well, ignores it.
Pretty much.
How is that biologically possible without the virus destroying the host's cellular tissue?
It's a marvel of evolutionary biology, really.
Right.
Over thousands of years, the virus and the deer mouse have reached this immunological equilibrium. The virus replicates just enough to survive and shed, but it doesn't trigger the mouse's immune system to attack its own tissues.
Wow.
Yeah. In humans, the severe lung damage of HCPS is largely caused by our own immune system overreacting. We experience a massive inflammatory cascade, a cytokine storm, that basically destroys the cellular lining of our lungs while trying to kill the virus. But the mouse's immune system exhibits tolerance rather than aggressive clearance.
So to study this, VIDO is taking on the logistical nightmare of establishing one of the only live deer mouth breeding colonies in North America inside a high containment facility.
Yes, which is no small feat.
I can imagine. Is the ultimate goal there to decode the mouse's immune tolerance? Like to figure out exactly which cellular signals keep the inflammation down so we can replicate that biological peace treaty in human patients?
That is the holy grail. If we can develop therapeutics that mimic the deer mouse's immune regulators, we can calm that human cytokine storm, preventing the lungs from filling with fluid while antiviral drugs clear the infection.
That would change everything.
It really would. And furthermore, Vito isn't just studying the mice. They are actively developing next-generation medical countermeasures. They're designing mRNA and protein subunit vaccines specifically targeted at Hantavirus cardiopulmonary syndrome.
Oh, like the COVID vaccines.
Exactly. The same foundational mRNA technology that taught our bodies to recognize the spike protein of COVID-19 is now being engineered to teach our immune systems how to safely neutralize the lipid envelope glycoproteins of hantaviruses before they can invade our lung tissue.
Man, it is incredible to see how all these disparate scientific threads are just weaving together. You have ecologists mapping the habitats of wild shrews with Project ARHA, French virologists mapping the physical locks and keys of the viral engine, and Canadian researchers breeding wild mice in level 4 containment to steal their evolutionary immune secrets.
It demands a completely multidisciplinary global approach. Because, as the MV Hondius outbreak proves, the virus is highly adaptable.
Yeah.
It only takes one rare mutation, like the Andes strain's ability to spread via person-to-person respiratory droplets, to turn an isolated environmental spillover in Patagonia into an international public health emergency on a cruise ship.
Yeah, let's really bring all of this into focus. Hantaviruses are not some obscure local curiosity. They're a globally distributed, environmentally driven threat presenting two distinct faces.
Right.
You've got the kidney-corrupting Old World strains and the highly lethal, lung-attacking New World strains.
Right.
And the 2026 cruise ship outbreak is a pretty stark warning that the rules of transmission are not set in stone.
But the global scientific community is rapidly closing the gap. From mapping the wild reservoirs to designing custom mRNA vaccines and targeted antivirals, our capacity to predict, prevent, and eventually cure these zoonotic diseases is accelerating at an unprecedented pace.
And why does this matter to you? Because as human infrastructure continues to bulldoze further and further into wild spaces, zoonotic diseases are no longer faraway problems confined to remote forests. The boundary between the wild environment and human society has completely disappeared. You can book a luxury cruise to the tip of Argentina, assuming you are protected in a highly engineered bubble, but that bubble is an illusion. We share this planet right down to the microscopic level, and we are inextricably linked to the ecology around us.
We absolutely are.
Which leaves us with one final, provocative thought to mull over. For decades, human medicine has tried to fight emerging viruses by focusing almost entirely on the humans who get sick and die from them. But what if the ultimate cure for the next devastating respiratory pandemic isn't going to be invented from scratch in a human hospital, but is actually hiding right now, perfectly encoded in the immune system of an asymptomatic deer mouse running through your own backyard?